Welcome back to ECE 320A. In this particular video, what we want to do is actually derive the Laplace transform of an integral. Here's the notation that we are utilizing. We're saying the Laplace transform of what's inside the curly braces, and in this case, it's the integral of some arbitrary waveform, little f of tau. So we're integrating f of tau from 0 minus to t, and we want to know what's the Laplace transform of that. We've replaced that information, that signal, which is in a blue box now inside our Laplace transform definition, and we want to now integrate or find the Laplace transform of this integral, which is in the blue box. Really what we would like to do is get rid of that integral inside the integral. If we just had integral of f of t e to the minus st dt, it would look like the Laplace transform definition of just the Laplace transform of f of t. And how do we sort of start knocking down this integral inside an integral? We can do that by integrating by parts. In this particular case, if we let this particular waveform, which we are trying to find its Laplace transform, if we call that v and call what's remaining dw, then by integrating by parts, we can actually reduce this down to something that looks more familiar. Here we're defining v of t to actually be the integral from 0 minus to t of f of tau d tau. That's tau is our variable of integration from 0 minus to t. dw is now e to the minus st dt. That's our differential. And we can find dv by differentiating this integral with respect to t, but that's now like evaluating the integrand at the upper limit, which is f of t, since it's a differential dt, and now what is w? If we integrated dw, that's now minus 1 over s. We're integrating with respect to t, e to the minus st. This is now our definitions in the integration by parts formula, where the integration by parts formula is saying we want to take the integral of v dw and rewrite it as vw minus integral of w dv. So let's now do that. This expression, so maybe I can enclose this. If I now enclose that, I now have this particular Laplace transform of an integral equal to vw, and v is now the integral from 0 minus to t, f of tau d tau. W is now minus 1 over s e to the minus st, and we now need to evaluate that at t equals 0 minus and infinity. Here is our v, and here is our w. And now we subtract from that the integral of w dv, which is the last part of this integration by parts. We're now subtracting the integral from t equals 0 minus to infinity of w, which is right there. So that's now minus 1 over s e to the minus st dv, which is actually f of t dt. Here's dw, and there was W, and here was dV. So we have VW minus the integral of W dV. Let's now evaluate the first term at the upper limit and the lower limit. Doing that, we can now say that we are integrating, or we now evaluate this at t equal infinity and subtract from that the expressions evaluated at t equals 0 minus. So now we have this integral from 0 to infinity of f of tau d tau times minus 1 over s e to the minus s infinity. That's now the upper limit. And we're assuming that this function is well behaved. So we're assuming that this piece right here is bounded. And we will then see that this second term, e to the minus infinity, is vanishing or going to 0. So that's now the upper limit term, which is now 0. We now need to subtract from that this first piece evaluated at the lower limit, which is 0 minus, and we have a negative sign in here. So subtracting and pulling that minus sign out allows us to say we now can have plus the integral from 0 minus to 0 minus of f of tau d tau minus 1 over s e to the minus s 0. This is now 1, the second parenthetical, or the second term in the second parenthesis, but now we're integrating over nothing from 0 minus to 0 minus. This first term now vanishes, and we're left then with trying to evaluate this remaining piece of our integration by parts. We can combine the two negative signs or factor out the interior negative sign, and now we are ending up with plus this integral from t equals 0 minus to infinity. And in fact, we can factor out the 1 over s because that's not a function of time t. So let's go ahead and do that. We now have this 1 over s out front. We have f of t scaled by this exponential e to the minus st dt. And I hope that it's starting to look familiar, that this particular term, not including the 1 over s factor, but the term that I've tried to bracket is now just the traditional Laplace transform of this arbitrary function f of t, and we've now derived then the Laplace transform of an integral is 1 over s times the Laplace transform of the original waveform f of t unintegrated. Or we can now say that the Laplace transform of this integral from 0 minus to infinity of f of tau d tau is equal to 1 over s f of s. And that will become useful when we start Laplace transforming dynamic relationships, and in particular when we start Laplace transforming integrals, we'll now be able to put those into the frequency domain by simply dividing by s.